Hello, everyone. Thank you for joining us for today's webinar. We'll get started in just a moment. Hi, welcome to those of you coming in. We're just waiting to give everybody a moment to join the session, and we'll get started in a few seconds. All right, hello, thank you for joining us for today's webinar in our Quick Quake briefing series with EERI's Northern California Regional Chapter. And this one is on the 7.5 magnitude earthquake that struck Japan on New Year's Day this year. Before we turn it over to the chapter and presenters, I want to take a moment to talk about EERI for those of you who are unfamiliar with us. The Earthquake Engineering Research Institute is the leading nonprofit organization that brings together people from a wide range of disciplines and fields around the world, working to understand earthquake risk and advance earthquake resilience. So you can find out more about us at our website. I'll put that in the chat later. And we encourage you, if you're not a member, to join us, including we have international affiliate membership options, student memberships, and a wide range of opportunities to become engaged. I also want to remind folks that our annual meeting is coming up soon in Seattle this April. It's going to be a great event. That QR code or that URL will take you to the website and the registration page. And I want to remind folks, if you've been thinking about registering, that the advanced registration deadline is coming up on February 29th at the end of next week. So if you want to get the best rates, and if you want a secure spot in some of the excellent reconnaissance workshops and the reconnaissance field exercise we're planning, now is the time to make sure you get your registration in. And so with that, I will turn it over to Richard McCarthy, who is the president of our Northern California Regional Chapter.
Thank you so much. I'd like to welcome our speakers here today. We're very interested in what you have to say. Our condolences, sincere condolences from our chapter to the people of Japan for the losses they've suffered. But hopefully we can learn some lessons from what you're going to present to us today. And we have to admit that we're having problems for their own legislature here to implement seismic policy. And so our chapter is working hard to get a champion, if you would, to try and carry some of our legislation to prevent losses like you had in January 1st. So we're very interested again in what you're going to present, and we're going to take some of that information and use it for our argument with our legislature to implement some policies. So again, thanks so much. We're looking very much forward to what you're going to say today. So I'm going to turn this over to Bruce Mason, who's going to introduce our speakers today. So again, thank you very much.
Thank you. Welcome to our briefing on the magnitude 7.5 earthquake that struck Japan earlier this year. My name is Bruce Mason. I am one of the board members for the Northern California chapter, and I will be serving as your moderator today. Now, our briefing program is a free program. Anyone can view them. Our goal is to share information as well as develop a method where people can get contacts with researchers and engineers throughout the world. Now, if you're a member of EERI, then you will receive notifications of future briefings. But if you're not a member, you can also get on our mailing list. And how you do that is to send me your email address to the address that's shown on the screen. Now, all of our briefings are available on the YouTube channel, and there's about 20 of them available. Go to YouTube and then just search on Quick Quake briefings, and the list will come up, and you can look at our previous briefings. Also, both of our speakers today have kindly provided their slides, and they will go into the clearinghouse for this earthquake, the EERI clearinghouse. So you'll be able to see that as well. So now on to today's briefing. The earthquake struck in the afternoon of January 1st on the west coast of Japan. It had very strong ground shaking. Permanent peak ground accelerations of over 1 G were recorded. There was extensive liquefaction, landslides, ground subsidence, uplift, you name it. It was a textbook with regard to geotechnical issues caused by earthquakes. There was even a tsunami that had a wave height over 10 feet. This earthquake damaged or destroyed over 50,000 buildings, and the preliminary estimate on direct damage costs was approximately 18 billion US dollars. That's billion US dollars. There will be many more seminars on this very significant earthquake, and we will be covering just 2 topics today. We're very excited to have 2 terrific speakers joining us from Japan. The first will be speaking about the strong ground motions that were recorded during this earthquake, and our second speaker will be talking about the spectacular geotechnical aspects that they observed. Both of our speakers did extensive field work immediately after this earthquake, so they have first-hand experience. And we plan to have another briefing soon that will deal with buildings that are damaged and perhaps transportation systems, so stay tuned. Here's the format for today's meeting. It's about a 60-minute program. Each of our speakers today will talk for about 20 minutes each. Then the rest of our time will be devoted for questions and answers. We encourage questions from the audience, and how you do that is you'll hit the Q&A button at the bottom of your screen, type in your question, then our past president, Volkan, and you see him there, will go through these questions, then he will come back later in our program and pose the questions to our speakers. Now, we know we might have more questions than we have time. So both of our speakers today has kindly provided their email addresses, and they'll be shown in their presentations. So you can email them directly with your questions, and they will try to respond to your questions in the coming days. Now, I would like to introduce our first speaker. Our first speaker is Dr. Hiroyuki Goto of Kyoto University. He will present on the strong ground motions recorded during this earthquake. Dr. Goto, please proceed.
Okay, thank you very much for introducing me. So I will share my screens. Oh no. Yes. Is it okay?
Yes, we see it good. We see it.
Okay. Okay, thank you very much for organize this kind of very interesting quick briefing. So this is Hiroyuki Goto. I would like to talk about strong ground motions of these earthquakes. So thank you very much for organizing this quick briefing, and also the organizing and operating the strong ground motion networks of the Japan Meteorological Agency and National Research Institute for Earth Science and Disaster Resiliency. So let me show up the brief quick summary about this Noto Peninsula earthquake. The earthquake occurred in the afternoon in the local time on the January 1st of this year. The place of the earthquake located in the Noto Peninsula that is located in the middle part of the Japan. The important point is this epicenter is located on the tips of the peninsula that is very difficult to access from the mainland of the Japan, but it has a very important significant city there located, for example, in the Wajima city and Suzu city there. About the population is 150,000 of the population there. The aftershocks of this earthquake is distributed along about 150 kilometers, meaning this length is almost covered with the main source fault of this earthquake. So if we focus on the epicenter location on the tip of the Noto Peninsula earthquake, Noto Peninsula, but the main fault is on the over in this entire region of the Noto Peninsula is covered by the main fault zone, meaning the cities in the Noto Peninsula is almost on the source fault. That is very important aspect to understand what occurred in this earthquake. So in this region, we have several seismic activities after the 2007. So in the first significant event in this region is the M6.9 event in 2007. That was occurred in the western side of this Noto Peninsula areas. And this blue dot is aftershock region, and that is covered almost in the western region of the Noto Peninsula. And 10 years later, some interesting point of this earthquake is the earthquake swarm started from 2020s. The earthquake swarm I plotted here as a gray dot. That earthquake swarm continues almost 3 years. The significant event within this swarm is M6.5 that was occurred in the last year. That is not clear why this kind of the earthquake occurred in this region, but some researchers said some fluid injection is an important reason to understand the earthquake swarm. But anyway, this earthquake occurred in the 2024. It's almost overlapped within this region, and also almost covered with the seismic region on the 2007. That was not like a small earthquakes. That is a quick summary of the earthquake here. So now move on the ground motion of these earthquakes. So we observe a very nice ground motion record organized by NIED and JMA. The peak ground acceleration observed here is exceeding several stations exceeding 1.0 Z. The most significant earthquake peak ground acceleration observed here, KNet ISK006, that was 2.78 G, almost less than 3 times larger than gravity acceleration. Also observing large peak ground velocities that are about 159 centimeters per second, that was observed here in the KNet ISK005. Also observed large ground velocities here in the Suzu City ISK002 and Wajima City 1.23 meters per second. So this kind of the very large ground motion is very important in the aspect of the ground motion. So now compare with this peak ground acceleration and peak ground velocity with the conventional ground motion models. The left-hand side here is the peak ground acceleration, and the middle diagram is the peak ground velocities. That was compared with the ground motion model with this thick line with a standard deviation line. Almost all the records following the ground motion model, then this earthquake is not like a typical, this is almost a typical and standard earthquake, I think. So now let's take into the earthquake ground motion record in detail. This diagram is showing the velocity waveform along these thick lines. The here, 0 means almost close to the epicenter of this earthquake. Of course, this trace almost on the fault line. Therefore, this ground velocity record is a kind of the history of the source process. The significant phase observed in the epicenter region is about the first large phases here. That was traveled through this in the western side, and also in this record, including another large phases. So if I trace this phase, they are coming from this western side. This means that there are at least two significant phases that is very related to a kind of the asperity or large strip region of the source process. That means, for example, in the at least, that first very large strips occur in the tips of the Noto Peninsula, and also another large strips occur in the western side of this Noto Peninsula. That is a very important point, especially in this region has a very long duration of the earthquakes. Earthquake ground motion was observed. So at this moment, we have several insights about earthquake source process and earthquake histories. So another colleague in DPRY estimate the source process. That, for example, here we observe that two fault is activated instantaneously in these earthquakes. The first started in the rupture from the earthquake and then provided to the west. Then that was the second rupture occurred here, and then observing large ground motions. Also, together with this earthquake, another earthquake provided to the northeastern side, and then observing a large ground motion. So, and also the very large cluster deformation was observed from the GNSS data. Now this, in the almost close to the epicenter region, we have 2-meter uplift, and the western side that is very consistent with the location of the slip areas, that observing a very large 4-meter uplift here. So now let's into the ground motion records. So first, I'll introduce the Toji side. Here, observing 2.78 Z of the peak ground acceleration. So this is accelerogram. So we are observing a very large ground motion acceleration in the east-west component. Here is the response spectrum. So you can see the very large acceleration response in the about 0.2 seconds of the period. So fortunately, we have So now we explain about what kind of the situation around the location of the site. So here is a very close, a kind of shed around this station. So we can see a very moderate and minor damage on these buildings. And also here is a station. So we can see a very minor damage on the embankment. So not only this photo, so we cannot see any kind of the very large ground motion damage on this site. So that was probably related to the period component of the ground motion. Fortunately, we have another ground motion record away from 3.0 kilometers away from this ISK 006 stations. Here, blue line is the acceleration response of these stations. That was probably very different of the frequency contents. So you can see very large amplification within less than 0.5 seconds of this site, meaning this large peak ground acceleration is related to the short period component site response of these KNet stations, I think. It needs to be more detailed analysis to why this kind of the amplification occurred here, but that is very important point to understand the large peak ground acceleration, this station. Okay, now move on to another site, Wajima site here. This KNet site observing this kind of the velocities. So here is the acceleration response of this ground motion. So this observing are almost following the same levels of the this acceleration response with JR Takatori record that was observed in the 1995 Kobe earthquakes. So surrounding this area is very large building damage and several another kind of the lifeline system or any kind of the damage here. For example, in the top down of the buildings, and here you can see a very significant damage on the wooden building houses. So in this ISK03 is located in a relatively good site conditions, but that with observing another ground motion site 1 kilometer away from this site that was located in the soft soil grounds. You can see the difference of the acceleration response here. The difference is significantly longer than 1 second of the response spectrum. This red line is very, very strong ground motion, meaning this soft soil ground is very affected to the building's damage on this site. So now I take a spectral ratio of these two records, not only this earthquake, we can summarize the several ground motion records with two. Then you can see some significant site amplification within the 1 second in the weak motion. But important point of this earthquake, this is red line here. You can see the site response shifted to the longer than the weak motion. That is enhanced 2 seconds of the ground motion, the site response. That is because of the nonlinearity, I think. It should be more detailed analysis required, but I pointed out the nonlinear site response is very dominant in this region. Okay, another site, analysis site is located here. This response spectrum is very, very high levels. So we almost following the JR Takato record in this site. So this area is also damaged in the buildings and the houses. So you can see a very important significant damages. In this site is also very interesting point is observing two different earthquake records. That is ISK 015. That is located in the stiffer rock site, not rock site, but stiffer site. Then you can see the difference in the spectral acceleration. So in the site of the ISK 005, observing larger less acceleration response longer than 1 second, as well as the Wajima site. So in the site, amplitude difference is maybe affected to the difference of the damage of the structure and the buildings. I use the same way to organize the weak motion to the large motion of the spectral ratio. So the weak motion, say the difference of the site amplification is seen in the 1 second almost, but that was shifted to the longer period in this large earthquakes. This means that this site is also affected by the nonlinear site response. That is the very important point to understand why this 1 or 2 seconds of the ground motion component is enhanced at this site. So I will conclude my presentation. The earthquake aspect is almost entire region of the North Peninsula is located above the source faults. That is a very important point. And also multi-wave groups are observed near the epicenter, then the resulting in over 40 seconds of the duration of the ground motion. The 2.78G of the peak ground acceleration observing the Kenneth Toji site, that is ISK06, but that is because of the very short period component enhanced because of the site response of the site. On the other hand, the Wajima and Anami's downtown observed significant building damages that is very associated with the longer period component about the 1 second. That is because of the nonlinear site response in that region. I skip this presentation in the situation of the Suzu site and ground motion there. So that is the we need to discuss about the detail about in near future. So thank you very much.
Thank you, Dr. Goto, for a very enjoyable, informative presentation. I was very impressed with the quality of your slides. They are very good and they will make for a great review for people in the United States. Thank you.
Thank you. Thank you very much.
I would like to move on to our second speaker today, and this is Dr. Masataka Shiga of Nagaoka University. He will be presenting on the spectacular geotechnical observations that were made following the earthquakes. Dr. Shiga, please proceed.
Hey, can you see my slide?
Yes, we can see your slides.
Okay, thank you very much. So thank you for inviting me to speak today in this EERI seminar. It's an honor to share the insights of the devastating ground impacts due to the 2024 the Noto Peninsula earthquake. So I'm Masataka Shiga. I'm an assistant professor of the Department of Civil and Environmental Engineering of Nagaoka University of Technology. And first of all, I created some 3D models based on the UAV survey or omnidirectional cameras. So I uploaded those 3D models to my Sketchfab collections. So please visit if you want to see it. Please visit this URL or the QR code. Elizabeth, can I also add that this URL in the chat box?
Yes, I'll share.
Yes. So let's move on to the slides. So first, I would like to explain the geotechnical damage types due to this earthquake. So first, the ground damage caused by this earthquake can be broadly categorized into 4 types. So the first is the damage to the port facilities. This one includes actually both those caused by the crustal movement and those caused by the strong ground shaking. And the second one is that liquefaction, liquefaction-induced damage, or let's say the lateral flow on the dune slopes or old river channels. And also the sand ejection were found in many places in the affected areas. And the third one is that slope failure at both man-made and natural grounds. So here is the regional map of the affected areas. As you can see in the left side, the epicenter is located in the northern part of the Honshu Island of Japan. And actually, the detailed talk on the earthquake ground motions was already given by Professor Goto, so I will skip some parts. And in the right side figures, the light red color shows the severely affected prefecture, the municipality of Japan, and the dark red colors is the location that I will introduce in the latter slides. And an important point is that fact that in Uchinada, which is right here, and Niigata, which is right here, and where ground deformation associated with liquefaction occurred, the PGA was around 150, from 150 to 200 Go. So these places are not located in one of the most severely shaken areas, which is how can I say? Which is right here around the Noto Peninsula areas. So
Drop. Maza, please proceed. There was a freeze.
Freeze.
Please proceed.
Okay. Which slide are you seeing now?
We're seeing the surface displacement by GIA of Japan.
Okay, that's correct. So I'm going to talk about their surface displacement by insert analysis. So Geospatial Information Agency of Japan collaborated with JAXA, and they conducted the insert analysis to obtain the vertical and the horizontal displacement with the use of the AROS2 sensors. As the red color indicated in the left side figure, in-cell analysis has detected approximately 4-meter vertical uplift and the 3-meter horizontal westward displacement by using the in-cell analysis. So because of this huge vertical offset, the western side of the Noto Peninsula has been uplifted. According to the previous report or the previous articles, the western side of the Noto Peninsula has been uplifted multiple times in the past to form multiple marine terraces. And the earthquake caused a maximum uplift of 4 meters in the crustal deformation, and which causes a new marine terrace. And this crustal uplift caused the many port facilities to be reduced in the depth, or the seafloor to be exposed in, as you can see in the left side figure. This is the Kaiso fishing port, Shika in Ishikawa. And apart from this crustal deformation, the usual, how can I say, typical open cracks or uneven settlement of the quays or port facilities were found in many places around the Noto Peninsulas. And then I will move on to the liquefaction part. As the Niigata is one of the famous cities for the 1964 Niigata earthquake, which popularized the term of the liquefaction. As some of the participants may have seen this overturned apartment in some textbooks of the liquefaction or soil mechanics. So although this apartment has already been demolished as of now, but the area of the Kawagishicho, where those apartments stood, is still in the city center of the Niigata. And according to our investigations, while some sand ejector was found on the sidewalks or school grounds, but there was no significant damage to buildings as a result of the 2024 earthquake. And then this is the regional map of the Niigata. As you can see, the almost 150 kilometers away from the epicenter, the severe liquefaction damage was observed. Actually, these two figures shows the local topography around the Niigata areas. The left side shows the left side figure are derived. The left side figure is derived from digital elevation model, and the right side figure is the prepared by the GIAs, which shows the local old topographics. And there are two typical terrain features where liquefaction niche damage occurred in Niigata areas. One is the southern slope of the Niigata sand dunes, and the other is along the old river channel of the Shinano River. And according to the Wakamatsu 1992, the severe liquefaction, as I showed in the previous slide, was well observed in the northeastern part of the city, which shown as the white areas. The affected area by this 2024 earthquake was relatively smaller than that of that caused by the 1964 earthquake, but they have same topographic features, which is the slope of the sand dunes and the old river channels. And the value of the PGA slightly differs in the city area, but they ranges from the 90s to 180 gauss at the maximum. So on the Niigata dune slope, surrounding around the prefecture road number 16, was severely damaged. The general trend of the deformation is downward, with some opening cracks in the upper areas and back of the pavement like this in the lower areas. And these observations implies that the thick pavement or small artificial channel may block much larger sliding. And this is the photograph and the photographs from the another area of the Niigata city. And as you can see in the upper left pictures, there's a huge sand ejector blowholes, and it is the 4 meters in diameter and 70 centimeters depth by using the iPhone implemented LiDAR sensors. And the ejector was composed of the very fairly uniform sand. And some historical maps mentions that the Shinano River used to flow from south to north, and it was reclaimed in 1960s or 70s. And then I will move on to the another liquefaction cases. So another iconic ground deformation was recorded in Uchinada, Ishikawa Prefecture. And here is the local topographic map around the affected areas. The sand also in Uchinada, the sand dune is about 40 meters high and runs from the southwest to the northeast. And the affected area is located at the middle to rear ridge of the inland dune slope. And it is facing the Kahokugata reclaimed land, which were reclaimed in the 1960s. And the right side figure shows the local elevation map of one devastated area, Nishiaraya district. If we draw the elevation profile along A to B, then you can see there is a steep slope exists in the west side of the sand, in the west side, and they're following the gentle slope of in the right side. And this is the example of the damage in Nishiaraya. You can also visit the 3D terrain models in my Sketchfab collection. And in an elementary school, in the ground of an elementary schools, as I indicated as P1, the several lines of the cracks parallel to the dune axis in the closer area to the steep slopes. And if we go to the lower areas, as you can see in those two figures, you can see the lifted up road pavement of almost 1 meters. And this is the previous photograph obtained by the Google Street Views. That you can there is no, how can I say, the tilting or inclination of the road pavement, but it was lifted up right after the earthquake. So this is another actually those figures taken in another area of the Nishinada, but the one 2-story house with the cement mixing improvement had stood without apparent tiltings. But this is only the houses that I observed is still, how can I say, is still okay. So I mean, except these houses, there's no unaffected buildings. I mean, all the buildings were severely inclined or tilted. So the next topic is about the landslide in the north part of the Noto Peninsula areas. So this is the landslide distribution, the vector datas prepared by the GIA of Japan. And as you can see, there's many small landslide occurred around the northern part of the peninsulas. So some of the landslide caused some of the landslide broke the national or prefecture road, which was very important to supply the supply the evacuation vehicles, but it was already blocked. So according to the GIA of Japan, the more than 2,000 landslides, which are mainly composed of the pyroclastic, are made access to remote areas difficult. So this is the one good example of the of the landslide. So this is located there, the Notocho, and the, as you can see, right figures, there's a big crust of weathered rock, including the shot creek to prevent the landslide. So sometimes this kind of the blocking of due to the landslide were found in the Noto Peninsula, in the further area of the Noto Peninsula. Also, this 3D model is available on the My Sketchfab 3D collections. So if you want to, or if you are interested in, please visit this website. And another aspect of the geotechnical damage to the breaches is that breach approaches failures. So this is a very typical behavior of the geotechnical damage due to the earthquake. But in this earthquake, the bridge approaches with embankments offset vertically over tens of centimeters. So and this behavior may be partially because of the small bridges do not have the approach strap. And this is another reason to make access to remote areas difficult in the early restoration stage. Then move on to the local roads. There are many. The Noto area is the kind of the hilly mountainous areas, so they have the valley fields on the road beneath the road pavements. So small field had slided or settled towards the valley side, and they have sometimes we cannot access to the further areas because of this blockage. And also the land properties, the field valleys opened for the school or residential houses slided downward, and it causes a severe damage to the upper structures. So some reports mentioned that weathered field material or poor compaction may cause these kind of the failures. And also, another reason could be another reason for these slidings could be the approximately 14 millimeter per day precipitations the day before the earthquake occurred. So this is the brief summary of the presentations. So first, the damage to the port facilities caused by there are the damage to the port facilities caused by tectonic uplift and strong seismic motions. And those coupling behavior should be investigated more. And the second one is the liquefaction-induced ground failure, even up to 150 kilometers far away from the epicenter. And there are two iconic sites. The one is the Niigata, and the other one is the Uchinada. And in both cities, there's a big sand dunes, and the tail end or the middle, from middle to the tail end of the sand dunes, there's a huge liquefaction behavior, horizontal displacement or open cracks or vertical rifted dam. And in Niigata city, there are liquefaction cases of old river on the old river channels. And landslide or field valley failure blocks the access to the remote areas of the northern part of the Noto Peninsula. And subsidence or cracks at the embankment of the bridge approaches also made us unable to approach further inland. Yes, thank you very much. This is the end of my presentation. Thank you very much for your listening.
Dr. Shiga, thank you very much for an informative presentation. Again, I want to compliment both of you with regard to your slides. They are excellent, and they are all in English, so we can review them very carefully in the future. Okay, this concludes my part of today's presentation. I would like to turn control of our meeting over to Volkan, and he will take on the question and answer portion. Volkan, could you please proceed?
Thank you, Bruce. Thank you for the speakers. I think this was a very good presentation. You laid out all the observations very successfully. And now I would like to ask a few questions too. Some of them are from our audience and some of them are my own. So before we start, the first question, this is from our audience, this is to Hiro.
Yeah.
So Santiago is asking whether or not JMA stations or KNet stations have any quality or frequency response differences, because you have shown some figures where you were comparing them. I think Santiago want to make sure that they are apples to apples.
Yeah. And of course, they're not exactly the same sensor they used in the JMA and KNet stations, but they used acceleration sensor. The acceleration sensor, the instrument response is almost fairly nice in the frequency range that was interesting in the engineering point of view. So in this case, if we compare with directly with the frequency range 0.2 second to the 10 Hz, I think that is almost okay to compare with this frequency range. Again, if we have some difference in the frequency response in the JMA and the KNet station, but we can see some differences in the earthquakes by earthquake in the input motion amplitude. This, for example, in the nonlinear site response, is of course that is including in the center instrument. It should be the same with weak and large motion. Then I think the nonlinear site response is including in the site response, I think.
Great. How did you determine the stiff versus soft ground site? What is your model based on?
Yeah, for example, in the KNet site, we can use borehole data up to the 20 meter in depth. So, for example, in the case of the Wajima site, they have the very stiff rock site. They are provided the information about where study is about over 500 meter per second. For example, in the case of the Anamizu site, in the both borehole is available at the site from the KNet site. So they have quite differences in the VS30. Please, that is very interesting point, and please check it.
And probably the major finding that you have shown today was, especially at the Wajima and Anamizu downtown area, you have found that the site amplification is period dependent. In other words, longer periods seems to amplify a lot more than the short period or high frequencies. So that's quite interesting. So do you see similar observation in any other earthquake, or do you think this is somewhat unique in this sense?
Yeah, sometimes this kind of the observation we have observed, but sometimes that is not directly. For example, within the very small town, we have only one seismic sensor is located in usually cases. Then after the earthquake, we investigating, for example, using the temporal observation of the seismometer, and then we will estimate that kind of situation. Of course, we can summarize this kind of things and another earthquake. But this time is very important thing. We can directly observe this kind of nonlinear site effect in very directly related to the building damages. That is an important point. Then we need to more detailed analysis about that.
Yeah, yes, you beautifully showed not only the station response, you also shown the damage response from that impacts, which is, I think, very interesting. So let me go to Masa, and let me ask you, I think one of the striking things that you have found was at the distance of 150 kilometers, and if I calculate this correctly, about 0.1 G or 0.2 G shaking, that will be 100 gal or 200 gal roughly, right? So at that shaking level, you start seeing liquefaction. That's quite interesting. That we done a study a long time ago about Christchurch, and that 0.1 G was roughly a threshold for liquefaction damage at that case as well. So do you think this is somewhat unique or unusual for this particular event, or do you think this is something that we should consider regarding with any earthquake that we are dealing with?
So the map, so the map, yeah, I understood your point. So the 0.1 G or 0.2 G is kind of the threshold of liquefaction occurrence. So in the 2011, the Tohoku earthquake,
Yes.
which devastated in the Kanto region by the liquefaction behavior, actually the PGA level is the almost safe, 150 or 200 gauss. So by, how can I say, considering that situation in the Tohoku earthquake, the ground can be liquefied in general. And also I'm now correcting the borehole or SPT data set in the database of the, how can I say, the municipalities. And then the liquefied area in Niigata city is quite deposited quite loose and up to 10 to 15 meters, which almost SPT annual is almost a 5 or less than 5. So that's kind of the typical ground structure, and also the one of the reasons to cause the severe liquefaction in Niigata area.
Did you see any similarity when it comes to landslide or other type of ground failure? Did you see any shaking threshold for these failures to occur?
I didn't conduct the detailed analysis up to now.
So that could be interesting to see if landslide is also somewhat has a like threshold to be activated. So all right, let me just go through other questions. So this could be either one of you. This is from Eduardo Miranda. He's first thanking great presentations that you have provided. And the question is about to Professor Shiga on the building near Wajima Station that overturned pretty much as a rigid body in a similar fashion as it happened in Niigata in 1964. Is this building a post-1964 building? And if so, why a shallow foundation was used?
Yes, thank you for your questions. And as I remember, this building was built right after the 1964, and this building is kind of the pyro supported buildings, but I don't know why how can I say, the pyro head and the basement of the buildings were detached and then overturned. Of course, the liquefaction could be one of the reasons, but maybe how can I say, the connection between the pyro head, how can I say, the pyro head in the base of the foundation, the connection between them is another, how can I say, factor to cause the kind of the overturning.
All right, so that's very interesting. So quick questions. Were there any observations of surface fault rupture or any damages to dams in these earthquakes?
Yeah, at first I will explain about surface fault. Okay, So the surface fault is almost located in if the surface fault appear in this earthquake, that is located in the northern offshore of this peninsula. That is inside in the sea. So that is not recovered for what kind of the dislocation there. But some researchers said some of the dislocation appeared on the land, but this is not exactly true or not. This is discussed at this moment. So we have no idea about what that is actually in the surface fault or not.
I see. There was a building that fell like a pancake. Were there any reasons announced for this kind of failure? Any information on that?
For your question means about the building damages, right?
Yeah.
Yeah, of course, I'm not sure about the detail of the building damages. So this is because, for example, at least we can say that several building codes is changing in Japan. After 2000, that was changing in the wooden houses was changing in the code. So after that 2000, not so significant damage was observed within this earthquake. That is a very important point. Then at first we need to discuss how to enhance this kind of the changing the house to the match with the 2000 code.
So just a quick follow-up on that. This is from Betty. What are the foundation types for the damage? In other words, residential buildings, are they all concrete slab on grade or any raised foundations? Person's asking.
I think this is because of the liquefaction, right?
No, this is regarding to, I think, foundation type. What are the damaged buildings standard foundation type? Is that a slab on grade? In other words, there's no like a crawl space, or raised foundation, what we would call in United States like a perimeter foundation. Do you have any information on that?
I don't have any quantitative data set, but according to my investigations, all the 2 stories residential houses was stood on the concrete slab.
Okay, so one person, Guillermo, is asking if any surface rupture. He's also asking whether there's a coastal uplift, and I think you have shown up 4 meters of
4 meters,
which is crazy, right?
Yeah.
A lot of
It's
very high, and also 2.7 G, 778 G is also very high observed value. I have a question about that. So you have shown a ground motion prediction equation and the observation for this particular earthquake. And I know that a lot of these observations are within the standard deviation. But it seems like we are now seeing, especially in Turkey and other places, and this earthquake, especially when you are very close to the fault, seems like we are observing these wild shaking. How much of this is can be considered as a part of the fluctuation of the ground motion model, and how much of it is actually maybe the mean value, right? So can you make some comments on that?
Yeah, that is very difficult question, I think. Of course, they have several factors to involve in the peak ground acceleration at the accepted recorded values. But under standard deviation, it supports in this kind of variations. Of course, 2.8 G that was observed in this earthquake that exceed as kind of the standard deviation value. But we cannot say about this is a probability situation in the variation. So we cannot say about what kind of range. But of the mean value about 1.00 or something kind of that in this earthquake in the theory, but
What was the 2.8 G
mm,
exceeded the mean value by 1 sigma or 2 sigma? Did you-
yeah, I cannot check what is how sigma, but that is exceeding 1 sigma, I can mention that.
Yeah. So, well, that's very significant. So let me check others. All right, more of them is coming. Um, is shear walls very common in Japan in the structures relative to floor area? Like what percentage of shear walls relative to floor area is used in Japan is the actual question.
Shear walls.
Mm,
Like in Chile, they have a very high shear wall
yeah,
percentage.
yeah.
Um,
I
is that a common practice in structures in Japan?
I'm sorry, I'm not familiar with the detail about the building
Shear wall.
structure. Yeah,
No
sorry.
problem. Um, I think there's one question, and I think you answered it. Most damaged buildings was due to shaking, not secondary hazards like fire or others. So that's obvious. So, and then, okay, this is interesting. John Anderson is asking that there's after thanking you for a great presentation, in the ISK 001 site, especially east component, has several similar shaped spikes on the record. Is there any explanation for these?
Yeah, okay, I will check it later. Thank you very much.
Yeah. And then
Yeah.
the second question, has it been possible to recover the static displacement from the strong motion?
Several researchers tried the static deformations, but of course, after the earthquake storm since 2020, so there are very GNSS temporal sensors were distributed in these areas. Then we can check using this kind of the actual deformation using the GNSS. Then we can compare with this correction data. Not to try to do that, but I think this is probably possible.
There's Charles Scott Horn is asking about travel advice. He's going to be in Kyoto in next 2 weeks. So he's not next 2 weeks, in 2 weeks. Yes, in 2 weeks. He's thinking to visit Noto Peninsula. Do you guys recommend him to do so?
Yeah, yeah.
Area?
Okay, please talk later directly.
Yes.
Okay.
All right.
Yeah,
That's a good answer.
yeah.
And the last question in my case, Charles just asked another follow-up. Older houses in Japan have pier foundations. Houses built last 60 years have perimeter RC foundations. Slab on grade isn't used in Japan. Shear walls are common in Japan. Thank you for the clarification, Charles. And then the last question is, during the swarm, did responsible officials request an estimation of maximum magnitude? And what the maximum magnitude, even if not requested? We have the previous example of the L'Aquila earthquake, all drama and everything. So were there any requests from the scientists to forecast?
Yeah, I think that is very difficult questions, I think. This is because, as I shown in the figure, this earthquake swarm is rotating within the tips of the Noto Peninsula. In this earthquake, in M7.5 in the moment of magnitude scale, that covered 150 kilometers in the length. That scale is quite different. So even if we discuss some of the large magnitude scales in this region, but is maybe less, not like the M7.5 earthquake.
Yeah,
So,
nobody would guess this would turn into such
yeah.
magnitude. I
Yeah.
agree. Well, this has been a fantastic presentations. I really, I am grateful for your time and answering questions candidly and preparing beautiful presentations for us. So before we finalize the presentations, I think I will have Richard McCarthy to say a few words, and then we will go to the.
I
Is
can
it?
just
Would you like to?
jump in
Yeah.
first very quickly. There was one question. Somebody was having trouble getting it into the Q&A. There was a question about and that was put in the chat about what would
Oh.
the duration have an effect on the liquefaction?
Oh, good question.
The duration of the strong ground motion for
Yeah.
the
Yeah, I believe so. The shaking.
Yeah, yes. Actually, that's also my interests. So compared to the 2011 Turkic earthquake, although the PGA is almost the same as the, how can I say, the Turkic earthquake, but the duration, of course, the duration is quite short. So I'm going to, I will correct the, how can I say, the SPT n-value data or the microterm, the shear wave velocity profiles to conduct some detailed the numerical analysis. What is the cause of the, and what is the effect of the short duration to the liquefaction occurrence. Thank you for your question.
All right. I think let's turn the microphone to Richard.
Thank you very much for those presentations. Very informative. I'm very impressed with the work that you've both done. And it reminds me of the great partnership we have between Japan and California in our attempt to reduce earthquake risk. And I thank you for the slides too. I back Bruce, what he told everybody was the quality of your slides is excellent. So even I could understand some of that, and that was very, very well done. Very well done. So I'm gonna turn this back over. Thank you very much, gentlemen, both of you. And we'll follow up with you on this as we attempt to have some earthquake reduction efforts more here in California. So thank you. I'll turn it back to Elizabeth.
Yes.
Great. So I just want to take a moment, just thank everybody on behalf of EERI, and also ask you to please complete the survey that'll pop up in the browser after this session ends, and you'll also receive it by email tomorrow. As I've mentioned, you can learn more about EERI at our website and find out how to join there. And then to find out about upcoming webinars, check out our Pulse newsletter, or you can find a page on that website that has upcoming webinars. And as Bruce noted, stay tuned because we do hope to have more webinars about the impacts of this earthquake on buildings and lifelines. We also will probably be having one on some new research on the Seattle fault risk that we hope to have before the annual meeting. And then finally, I just wanted to acknowledge and thank the support for this webinar series, which comes both from a grant from FEMA and also from EERI members like yourselves.
Okay.